I was muted, sorry. But also because we use that for space weather forecast. So we identify regions where technology is susceptible to damage during geomagnetic storms, for example, like the South Atlantic anomaly, where satellites have to turn off going through that to protect the technology. So we do need to understand the Earth's magnetic field in a general way for present applications as well. And we use the magnetic field as well for navigation, the classical magnetic compasses or navigational systems in planes. And we can also use the magnetic data on the surface to mineral exploration and, resources in a general way. And the more we observe, the more data we acquire, more we tend to understand the magnetic field, right? The more we grow in the understanding of it. But the problem is, Earth has 4.5 billion years old, and all the data we have from the past is from the surface. So how do we get information for what happened deep within the Earth? So paleomagnetism and numerical modeling are the only two possible methods that can lead us to understand what happened deep within the Earth in the past. And paleomagnetic data is giving us an idea of what was happening on the surface based on a process that has its effect generated deep within the core. So that's why we care about understanding ancient magnetic fields. And of course, the present is the past, the present is the key to the past, and the rocks, they will have magnetic minerals. Those magnetic minerals will have spontaneous magnetization, and the magnetization carried by those minerals will have a direct relationship with the geological history of the rock itself. So how do we use that information? Well, if we think about the Earth and the magnetic field as a dipolar field, and then you have the lines coming out of the south and entering in the north, and then in here you have the magnetic moment in M, and then you have the inclination of the magnetization right here, here at the top of the image, and this is the latitude. And then if we take two components of the magnetic field, the horizontal and the vertical component, if we calculate the inclination of that, that will give us basically this very funky equation, which is the basis of the paleomagnetic sciences. So if you see this red curve right here, which is the graphical resolution of that equation, and then if you plot the paleomagnetic data of sea sediments from the last 2 million years, they all fit within that. So what that's basically telling us is the core of paleomagnetic sciences. If we know the inclination of a the magnetic inclination of a given rock, we can basically position that rock on the surface of the Earth. But we also know that's not that simple, of course. I'm just, simplifying a bunch of stuff here. But we use that data basically to reconstruct the positions of the continents in the past. So we can go all the way back in time and use the paleomagnetic data to constrain how the continents were moving around. And, that's pretty much the only quantitative method that we have to position the continents in the past. But the intensity of the magnetic field also tells us a very interesting story, because it is linked with the generation of the Earth's magnetic field. So if we look at how the paleointensity shifts, within the past geological history of the Earth, we can see some tendencies. For example, this decay in the paleointensity about 500 million years ago, which some researchers believe to be related to the nucleation of the inner core. It's not, a general, consensus. People are not entirely sure of that yet, but it's one of the possible explanations for that. And because the Earth's magnetic field is essential for life, we can actually connect it to the atmospheric protection and also to, the evolution of life itself. Because if we are protecting the Earth, if we don't have a magnetic field protecting the atmosphere, we're going to have a lot of radiation coming on the surface. We're going to have atmospheric erosion caused by the solar winds, and life is directly affected by that. So, for example, there are some researchers that try to pair complex evolution of life on Earth with the disappearance of the magnetic field or the weakening of the magnetic field during the Cambrian times. And in fact, we don't need to go so further back in time. Actually, if we look at the South Atlantic anomaly, and if you look at the paleointensity data that we have like up to a few thousand of years ago, we can look at how this anomaly has evolved. How this anomaly has evolved over time, and it tells us a story of how this anomaly has migrated over the past few thousands of years, and it can, we can use that information to understand, what we can expect from this anomaly. Will it ever disappear? Is it going to become like even stronger, and on and on. But we can actually go beyond Earth itself. We can look at meteorites and the paleointensity meteorites to understand the magnetism of the solar nebula, and that would tell us how rocky planets get together and the influence of the magnetic field in that process, and also to date the birth of our own sun, because when the protostar becomes a full star, the magnetic field increases, so we should see a peak in paleointensity in that as well. So paleointensity and paleomagnetism can tell us a lot, and that's the basic introduction of why we care about magnetic fields in a general way. So brilliant, all we need to do is to measure the remanent magnetization of a rock, right? Well, no. So the problem is, in a rock we have all different kinds of particles. We have small particles, we have big particles, and the magnetic properties of these particles will be directly influenced by the shape and the size of these grains. So if we see like a scale here with grain sizes, and where we're going to have dozens of nanometers and microns to millimeters in here, we can divide this into different kind of magnetic behavior. So we have single domain states in which we're going to have a uniform magnetization. So the magnetic momentum inside the particle is going to be stable in one direction, and this is going to be a highly stable particle. And we have multi-domain states, which happen when the particle increases in size, the energy is too big, and then you have two domains opposite to each other to negate that energy. And this is a highly unstable grain. But we also have the things in between. So for soft ferromagnetic minerals, we have this funky state called Vortex-state, which is attributed to high stability as well. But if you go back and, to grain sizes below the single domain, you're going to have uniform magnetizations, but they are not stable. So we have these complex kinds of behaviors that are included in grains in rocks. So not all of the grains are going to have high stability. We're not looking for all of the grains for paleomagnetic purposes. In fact, the single domain theory is basically derivated from Néel single domain theory, and the whole paleomagnetism is based on that. But the thing is, this theory tells us about a relaxation time, which is like how long the magnetization is going to be preserved, right? And it's basically related to this equation. So this is atomic frequency. Down here is the thermal energy. So we have the Boltzmann constant, the temperature, the volume of a grain, the magnetization saturation, which is basically how well aligned those magnetic moments can become when you apply a given magnetic field, and also by the fact that these magnetic minerals suffer hysteresis. So if we decrease the field intensity and then apply it to the other field direction after saturating the sample, we're going to have a full hysteresis loop, and then basically the field necessary to basically erase the magnetization is what we call coercivity. And I am explaining to you what magnetization saturation and coercivities are, because those are basically the two properties that will influence how stable a grain is. So if we have superparamagnetic particles, they are unstable because the thermal energy is much, much bigger than the magnetic energy. So they're going to like relax the magnetization really quickly. So if the samples are really, really, really small, they're not going to be stable at all. But if we increase the size a wee bit, they are going to become incredibly stable. They're going to go all the way up to billions of years in terms of the stability. But the thing is, what happens here in the vortex state? Because the vortex state is not included in the Néel single domain theory. And most of the stable natural remanent magnetization of the rocks is actually not associated with single domain. It's actually associated with magnetic properties that indicate vortex states. So we do need to understand a bit better about this, important domain states that we find in rocks. And although it can be directly observed with electron holography, for example, it's very challenging measuring the magnetic properties of these very, very small grains. And so how do we study these properties then, if we can't measure them very accurately? How do we study this vortex state? So we rely on mostly micromagnetic modeling. So for micromagnetic modeling, we need a geometry. So for that geometry, we discretize it into finite elements. So basically separate the grain in tiny regions. Then, to understand the magnetic properties, we have to minimize a function of energy considering all the anisotropy fields that gives birth to the properties of those grains. So we have exchange energy, anisotropy energy, demagnetizing energy. So we minimize the energy for that grain within those finite elements. And that allows us to access the magnetic domain states of these particles. And that also allows us to perform a bunch of simulations under different conditions of field intensities, temperatures, volumes, so we can basically try to understand how these particles will change their properties over time. Not over time, but over these different kinds of properties and conditions. So the micromagnetic solutions, for example, they have predicted the existence of the vortex state even before it was truly experimentally observed. And we have this kind of workflow of how they evolve. Usually they evolve from a single domain to a flower state, then to a single vortex state. So you're going to have one axis of the magnetization where all of the momentum is going to be rotated around, and then it can evolve then to multi-vortex states, the further we increase the size before truly becoming a multi-domain grain. So it's actually a transitional path. And the micromagnetic models have also shown us that these single vortex grains are actually as stable or more stable than the single domain grains. So the physics of the vortex state particles are much, much more complex than the classical neo single domain theory. So although they are very stable, we have some zones of grain sizes within the vortex state. They are stable magnetic grains. So we have this very complex range of behaviors, and we need to fully understand them in order to get really interesting paleomagnetic data and interpret these results in a consistent way. And to achieve that, we need to improve our micromagnetic models by looking into real grains in rocks. And we achieve that through nanotomography. So we have a bunch of different kinds of nanotomography. We have those that are related to electron tomography, which include TEM, STM, and focused ion beam. They have variable energies within themselves and, different resolutions, all of them. So in here, for example, you see that for TM, you're going to need ultra-thin samples, and you need higher energies, which will generate high scattering, meaning that we're going to have noisy data most times. And also we need ultra-thin samples, and ultra-thin we mean a few nanometers in length, which usually doesn't help us within these measurements. And then we have, for example, focused ion beam, which is a really good technique, but it has a nanometric resolution, but is a destructive technique. So the sample is going to be gone after you measure it. And apart from that, it only give you qualitative results. You're going to have contrasts. You're not going to know what you're looking at. You're going to just know that something is brighter than what's next to it. So you don't know exactly what magnetic mineral you're looking at when you're doing this kind of tomographies. So in here, for example, you have a Phibbs Lyson view in which you have a thin section, and then you cut a trench in that, and then you basically so what the Phibb does is to destroy the surface of a sample and keep imaging it. So then we stack those results together, and then you can just get the three-dimensional morphology of the grains within that given volume. But it doesn't tell you what it is. So you do need a few other techniques like imaging on the surface to do EDS to know if those grains are actually iron oxides or not. And then you can just micromagnetic model the behavior of these grains. We also have the tomographies that are related to atoms. So for example, atom probe tomography. In this case, what it does is to evaporate the surface of the sample and measure all the elements that are being evaporated in each single pixel. So it's a highly effective and really interesting technique. But the samples have to be extremely small. They are a few nanometers in size, and a few nanometers, like 10 nanometers by 10 nanometers. So that also doesn't help us, because that's going to put us, within the super-paramagnetic state usually. But we can have really nice results. So in this case, for example, this is a sample from a meteorite, and then they took a piece of this cloudy zone right here, and then you can see that in blue are the regions with the nickel atoms, and then the tiny pixels in red are iron, spread across the structure of it. So this is also a really nice technique, but also don't quite help with the micromagnetic models because of the size of the samples and the resolutions. Then we finally have the X-rays. And the X-rays, we have, the lab scale micro CT, which is really good because it has, conventional detectors that you can have your own lab, and it has a fast acquisition, and you can use large samples, but then you only have micrometric resolution. So you can't see the vortex-state grains that we're actually interested in, because you're going to have a pixel size of 500 nanometers or so, and so that doesn't help us a lot. So in here you have an example. So this is just like a view from the top, and then you see like a view from the depth, and then you see like a few grains spread, and the voxels, made out these grains, but all these particles would be multi-domain because of the resolution. And then we can use that, the information of the depth, for example, to understand the anomalies that are generated on the surface and measured by a magnetic microscope, like a QDM. So lab scale micro-CT is nice, but still doesn't have the resolution we're looking for paleomagnetism. And finally, we have the synchrotron-based X-ray tomographies. And to understand that, we have to go a little bit about what is synchrotron radiation. So it is actually an electromagnetic type of radiation, and it's generated when you have charged particles, usually electrons. They are accelerated near the speed of light, and they're forced to travel along curved paths by strong magnetic fields. And this is basically a visualization of how a synchrotron facility is. So within here, you're going to have a source, which is called a linear accelerator. So you just extract the electrons from like a copper wire, and you accelerated it in what's called a booster ring, and where it's going to reach nearly the speed of light, 99.9999%. And then it is transferred to a big storage ring. And then from the storage ring, it's taken into the synchrotron facilities, to the research facilities within the synchrotron. So why is it interesting? Because it has the synchrotron light has a broad spectrum. So it goes from radio waves all the way to gamma rays. And that means that how thin that ray can be is what we're looking for in the tomographic techniques. It also is extremely bright, and that means that we can see things with different contrasts more easily than we do in the lab, because you put in much more energy in that. And then he also has a bunch of much more complex and powerful detectors. This is the synchrotron facility in Brazil, which is called Sirius, and at this moment it is the brightest synchrotron facility in the world. They open for grant proposals every year for all kinds of different analyses you want to be, and if you get it, it's entirely for free, from sample preparation to analysis, so heads up. And also because we can have the energy tunability, meaning that we can look at specific energy emitted by specific atoms. And what that helps us with is, there's an example here in which we have a rounded particle, and then we can see the change in iron concentration from the borders to the center of it. And then when we look at the X-rays absorption spectrum of that in here, we can match, for example, this is actually a mixture between signals of magnetite and magnemite and hematite. So it's in between that, which tell us that we have a magnemite border rimming magnetite center. So we can look at specific compositions of minerals before going through the tomography itself. And how can we use the synchrotron radiation to improve X-ray tomography? Well, you can perform the same kind of analysis that you do for micro-CT, or you can use different techniques that the synchrotron, allow us to perform. For example, Ptychographic X-ray Computed Tomography, or PXCT for short. So what PXCT does is a method that relies on collecting overlapping diffraction patterns in the sample. So the radiation comes, it hits the sample in a given surface, and is going to generate a diffraction pattern. So we rotate the sample and keep collecting these interference diffraction patterns. And I'm just going to skip this because it's exactly what I said now. But what that basically does is, if we are collecting this scattering pattern, which is this thing right here, sorry, let me just go back. If we're collecting these diffraction patterns, that will allow us to solve this equation right here. This equation is called the full complex index of refraction. So we are recovering the phase when we're doing this diffraction, putting these diffraction patterns together, and also the absorption. The phase is related to X-ray refraction, and the absorption to X-ray absorption. So two different mechanisms related to how matter reacts when energy enters in contact with it. And the phase that we recover from it can be translated into something called electron density. So it's just a direct translation after we have it. And from electron density, we can recover Book density, meaning that we can effectively collect the density of the materials we are observing, which makes it different from the other X-ray techniques, because we're just looking at a given mineral with precision. We're going to look at pixels with small size, but we also know the density of the pixels we are looking at. So I'm just going to show you a few case studies. So we have these samples. This is from a paper that I published last year in Communications, Earth and Environment. And then we have these carbonate samples in Brazil. They are all remagnetized. So they are in these regions right here, along the Amazon and San Francisco cratons right here. And then you see that their poles are all together in this region right here, and far from where they should be, which is around here, if you would look at the depositional age. So we know that they have been remagnetized, and we know that they do have a very complex magnetic signature, but most of them are within the pseudo single domain region within the day plot diagram, for example. So we thought, why not trying to use this technique to understand these very complex, rocks? So what we see with some EDS analysis are some clay minerals that have suffered transformation. So namely smectite becoming illite. So in here you see the stripe right here of illite in the middle of smectite. So the reaction releases iron in the medium, and then magnetic particles can grow from that release of iron. And then we very often see magnetic particles, iron oxides, embedded along the clay minerals because of that. Then we took those samples, and then in here you see a thin section of it. And then just increasing zoom. Then we carbon coated it, we cutted a trench, then we cutted a pilar using Phibbs Lyson view. So we just go there and cut a pilar. And then we put that pilar in a pin, and then here you can see the scale. So the pilar has 20 microns from here to here. Then we went to the Swiss light source to perform X-ray ptychographic tomography. We got 650 different projections and 260 different images for both phase and absorption for this pilar. And then in here you can see the electron, you can see the phase, the tomography phase, going deep within the sample. So you've seen the changes as we go, deep. And then the gray levels are basically the different materials that you have within that. So we do a bit of processing to convert, again, phase into electron density, and then we can separate the different classes that we have there. So in this case, we have 5 different classes of electron densities. So we can then calculate the Book density of the material that we have there So we have separated all of the classes, and then we can like fully reconstruct the tomographic internal structures of these samples. So we have here those are the same panels. I'm just highlighting different things in each one of them. So in here you have in yellow the phyllosilicates, so the clays that we observed before, but we also have some hydrocarbon, along a few of the planes, and the iron oxides are all spread across it, and we have different sizes, different grain sizes and shapes for those as well. In here, just to show a bit of the variability of the sizes of the particles we're observing. Most of them were actually between 60 and 60 nanometers to 1,000 nanometers, so it's well within the range that we were expecting to find them in order to perform these micromagnetic models. So for the micromagnetic models, we look at the magnetic structure to understand a bit of the remanent state, but also the temporal stability of those. So looking at the structure, we saw all different kinds of domain states. We saw single domain states, we saw single vortex states in here, and we also saw this twisted S-shaped vortex states, that will depend on the shapes of the particles. But we also found some things that are very interesting. We saw some domain states that have the same, so we have some particles that will have many different possible domain states with similar energies. And why that's important is because the state that's going to be assumed by that given particle is given by the energy of it. If one state will be assumed if it has the lowest energy, and if you have a bunch of states with similar energy, you can assume pretty much any one of them, and I'm going to come back to that later to tell you why it's that important. But basically, it has implications for paleointensity, because when you're increasing the temperature, you can have a swapping between the domain states, and that will basically make your paleointensity experiment fail. But we also look at the temporal stability of these particles. So we calculated the blocking, we calculated the energy barriers for these particles, and we used that to calculate the temporal stability. And we got, that these very irregular shaped grains were mostly very stable, with stability surpassing the age of the solar system. But we got a few of them, this is one with 120 nanometers in length that is very unstable. And as you can remember, at the beginning of this talk, I talk about this region here that has low magnetic stability. So for equant magnetite particles, you'd go from 80 to 100 nanometers, but then in here I have a sample that's 120 nanometers and is also unstable. So what that's showing is irregularities in shape within that region can shift the zone a bit, further and backwards as well. But we also have particles, for example, they are within that zone that are perfectly stable. So again, morphology in this transition matters. And for the case study number 2, we decided to change a bit and go from sedimentary rocks looking at carbonates to actually sandstones to look at magnetofossils. So we were looking at, in this second case study, to the process of organisms crystallizing minerals outside of their cells, so biomineralization. So this is basically the earliest kinds of magnetostatic bacteria produce the earliest types of biomineralization. So in here you have these microorganisms that will basically generate these chains of magnetite along their bodies. And we know they are stretch all the way back in the geological history. And one interesting question is when did that start? So these organisms, probably some of you know that, but they can be found today. So if you go in the seawater and a few lakes, sometimes you're going to find this organisms generating this kind of chains. They are usually nanometers in size, the particles, so they are essentially single domain. And they are very equant in size. So you're going to have uniform particles distributed in the chain. They're a few nanometers in size. And they generate this, well, for many reasons. So first, magnetoreception. They can orient themselves in the water column, so they can rotate towards the magnetic field, and they can go from oxic to anoxic zones. But they can also use the energy from that for detoxification, And there are other possible functions that like still remain to be explored, even for example, electrochemical battery, because it's going to be moving from an oxic to an oxic zone, so you're going to have basically ions going back and forth and storing energy. And then a few years ago, we discovered these guys called giant magnetofossils. So we have these particles, they are much bigger than the ordinary magnetofossils that we find, and they have these very peculiar shapes like arrows and all this kind of thing. So basically they violate what we know for magnetoreception, right? Because we need small single domain particles, they need to be like all aligned. So what's the purpose of generating these giant magnetofossils? And the other question is, how back in time they go? When did they start to appear? So in order to respond to those questions, we look at samples from the Gunflint Formation, which is almost 2 billion years old. And in those samples, all the way down to like the 1949, 1950s, we found this kind of filamentous and coccoidal fossils that are interpreted as bacteria that did oxidize iron, but we didn't know, what was the purpose of this oxidization. So we took one of those samples, and we did perform the same technique, ptychographic tomography. And here you've seen a little video of that, the same thing, the gray levels, and then in here you've seen the segmentation. The blue is for voids, the green is for organic matter, and for orange, you're seeing magnemite. So it has been oxidized to magnemite. But then what's interesting here is that you have these structures, they are aligned, perfectly aligned, surrounded by organic matter. And when you look at the grains, you have equal sizes. Of course, they are overgrowth because this has been altered over time. This has 2 billion years old. So one question we asked here is it possible that these are giant magnetofossils and we don't know? So, oh yeah, this is just what I was saying. So what we did was to take one of the grains, the most well-preserved morphologies. We built a synthetic chains with different orientations, like we see for the magnetic bacteria today. And then we micromagnetic model the behavior. So the question here is, can giant magnetofossils or giant magnetosomes, which is usually formed by multi-vortex-state particles, perform the same kind of orientation towards the field as the modern magnetostatic bacteria do? And the responses we have, of course, is that we're going to have like this very interesting multi-vortex structures, but basically the structure will be aligned with the 1-1-1 axis of magnetite, which is not so surprising. But, and that, by the data that we published on PNAS, we showed that multi-vortex structures can also perform efficient magnetotaxis. So is it possible that, that's one of the, the reasons why this organisms crystallize these giant particles as well. And for the future perspectives, so using ptychographic tomography, we might possibly use this technique combined to micromagnetic models to understand, for example, the magnetization of rocks that carry very complex histories, so Archean rocks, for example. We can also use that to understand the mirror magnetisms of like meteorites, because if we image the phases, we can try to understand the different kinds of magnetic carriers carried by them and how they are stable or not. We can also apply that to astrobiology, because if samples returning from Mars soon, for example, we have any different possible particles that could be generated by organisms, we could try to use the same technique that we use for the magnetostatic bacteria to study them, but especially for magnetic microscopy. So in here I have one last example in which we've taken samples from, basically they are archaeological samples, they are tiles from the Jesuitic missions in Brazil. So the samples are from here. They have a very reversible, roughly very reversible susceptibility curves, and forks that indicate single domain to vortex-state structures. And they, Telier technique, it's basically giving really, really nice results with a very, very similar paleointensity. So we're using that as a possible way of testing a new technique, which is combining ptychographic tomography, magnetic microscopy, and micromagnetic models to try to generate a new paleointensity method. So the idea here is that we are demagnetizing the samples. So we have a thin section, we demagnetize that in the rapid system, we measure each step, we take it to the QDM, and we image the magnetic anomaly on the surface. And we do that for this, once we have the anomalies on the surface of the QDM, we invert the magnetic moments of each one of the anomalies. So we're going to have the magnetic moments of each one of the sources. So then we apply an ARM in the same steps that we have demagnetized the samples, and then we can build a pseudo array plot and basically take a pseudo paleointensity, a pseudo Telier of that, right? So in here is just a quick example, but for the whole thing section, we're seeing the AF demagnetization, we're seeing the AF demagnetization path going all the way and becoming stable right here. Oh, sorry. And you're seeing a viscous component here, but the stable component in the center going right where they're clustering right here. And in here, for the whole thing section as well, you're seeing NRM loss and ARM gain right here, and a pseudo-array plot with fitting from this region to this region, giving a alpha of minus 1.62. So this is for the whole thing section. Now we go to the QDM in a few regions. We image then between the same, so we're measuring this at the same time. We are demagnetizing in the rapid system and measuring the QDM. We are inducing in the RM in the rapid system and measuring the QDM as well, and inverting the magnetic moments using Fahira's approach. So here's just an example. You have the lead image just to see like a tiny region of the sample, and you have the BZ component in the same region. This is for the NRM. And then you apply stepwise magnetization, AF, the same thing we were doing before, and then you invert the magnetic moments. And looking like that, it seems very sparse, but I have to remember that this is a TRM. So the TRM, you're not looking at how clustered the magnetic moments are going to be. You have to look at the total sum of the magnetic momentum. And why is that? Because when a grain is acquiring TRM, the magnetic moment will not orient towards the field. This is a common misconception. The magnetic field of the particle is going to be along the easiest axis, the easy magnetization axis that is closer to the field. That doesn't mean that the axis is aligned with the field. So when you sample all of the magnetic moments, you're going to exclude the randomness, and then you're going to cluster the directions that are pointing closer to magnetic fields. And you're seeing that here, the sum of all of them getting closer to this black spot right here, and when you look, is exactly close to where we are looking at. So we are getting results from the thin sections that are closer to the results that we measured in the rapid system, which is telling us that we're going in the right spot. But we're not there yet. So this is just raw results. So we didn't do any filtering, any individual analysis, just looking at the raw results, summing everything and doing the pseudo-array plot for the data that we got from the QDM from one map. And you see here for a slope of minus 1.6, and for this region here, a slope of minus 1.5. So we are very close, even though we're not doing any filtering yet. So we are not looking at how well the fits were performed. We are not looking at the cohesivities. So what we're doing from now on is to do a better filtering of the whole process. We're going to look at applying IRMs in one way and then in the other to filter things that have like higher cohesivity, so we can exclude that. We're going to look at the grains for the anomalies to which the inversion didn't result in good fittings as well. And the ultimate goal is that if we perform a ptychographic tomography of one of the regions that we have mapped right here, so we cut a pilar, the same thing we did, we image then, we perform ptychographic tomography, and we do a micromagnetic model of the grains that are within the region that we have mapped by the QDM. we can basically change this parameter here by the micromagnetic modeling and get a correction factor, an exact correction factor, to transform relative paleointensity to absolute paleointensity. So that basically means if we succeed in the end, that we're going to have an absolute paleointensity method that doesn't require heating at all. Meaning that we avoid the problem of the multiplicity of domain states that is caused by heating samples. So that's the dream, and there is a big gap, and there is a big there are many questions to be sorted in this whole process, but this is the path we're trying to take. Can we actually use technology at its frontier to generate a new paleointensity method that won't require heating and will allow us to get better results for critical periods of the time on the geological history? And that's it. Thank you.
So this is looking very promising, but there are two things. First of all, you've got a time scale for the future. Would you like to estimate? Prediction is always a problem. We'd like to estimate it. Secondly, compared with doing a traditional method, it's rather more intensive.
Yes.
It takes a lot of stuff.
Yes.
Is it going to be practical for doing? I mean, obviously, there's been a thing in palaeomagnetism for some time of making the perfect measurement.
Yeah.
And then we find a whole load of things, and I've always gone looking at the data on the other approach, which does taking lots of measurements and letting the stats sorted out.
Yeah.
So do you think you're going to be able to, do you really think you're going to be able to do better? What kind of timescale and what cost?
That's a good question. Excellent question. A very annoying question. No. No. So here's the thing. Yes. So in terms of future perspectives, we're gonna get the tomography measurements for this same sample that I show you next month. So, but there is the whole modeling that takes time. So we're gonna have probably some results for that by the middle of this year, hopefully. But and then the second question, which is like, oh, it's very time consuming, would that replace classical paleomagnetic analysis? So the thing is, for classical paleomagnetism is the same over the past 20, 30 years. So how do we advance with that? We advance with that by looking at the microscale. And by looking at the microscale, we're having different equipments appearing right now. So the QGM is one of them, because it gives us the possibility of looking at individual sources. And then we have in labs all over the world acquiring QDMs or squid microscopes very frequently. So we have Harvard, we have Utrecht, we have here in the UK, I think there was someone bought one as well. Yeah, in Sao Paulo we are buying 3. So there are different labs acquiring this equipment because it's very promising for the applications. We can do a bunch of that. And the whole idea is that we were not going to need to perform the ptychographic tomography all the time. So the idea is we're doing this to use as basically a proof of concept, because what we ultimately want to do is to get the information that we're going to get from the ptychographic tomographies by basically looking at the fork diagrams. So we have a second project now that I am trying to carry on as well as a continuation of a Chinese collaborator, which is using neural networks to invert the grain size and distribution of particles from the fork diagrams. So if you do that, we have basically the micromagnetic solutions for all possible grain sizes and shapes in a given data set. Then we invert that from the fork diagrams, and then you're going to have the size and distribution of that, and then you can use the correction parameter for those kind of assemblages that the fork inversion is predicting. Is it going to substitute classical paleomagnetism? I don't think so. I think the idea here is that we're probably going to be using micro paleomagnetism to confirm things and to look at critical periods of the history of the Earth that we can't sort it for, like, general methods. For example, the Cambrian transition, that we have this crazy reversals happening in a very short period of time, and some data indicating low field intensities and other data indicating high field intensities. And so it's kind of like we have to look at this data more carefully, and we need a method that will allow us to not go through all the sum of the magnetic moments that we're seeing in a thick sample, but rather looking at the individual sources and tell us what history, and see what history they're telling us.
Okay, this is sounding encouragingly promising. Whether you manage it in 6 months or 6 years, I don't mind. But it sounds like there's going to be some numbers which will tell us more about things, which is cool. I like that.
Hopefully, yes. Thank you.
Please be more optimistic than that.
Thank you all for listening.